Welcome to the lesson on sampling distributions. Suppose a battery manufacturer needs to find the true mean lifetime of all the batteries produced in an hour. Quality control inspectors would simply measure the lifetime of each battery by draining it and then calculate the average. With this method, the company would know the truth about the population, but it would have no batteries left to sell. So instead of testing all the batteries in an hour, the manufacturer collects data from a random sample of 30 batteries produced that hour. The company's goal is to use the sample mean lifetime to estimate the unknown population mean. This is an example of statistical inference. We will use information from a sample to draw conclusions about a wider population. To make such an inference, we need to know how close the sample mean is likely to be to the population mean. After all, different random samples of 30 batteries from the same hour of production would yield different values for the mean. How can we describe this sampling distribution of possible x values? We can think of x, or the mean, as a random variable because it takes numerical value that describes the outcomes of the random sampling process. As a result, we can examine its probability distribution using what we learned in Chapter 6. Here are some more examples of inference settings. Each month, the Current Population Survey, CPS, interviews a random sample of individuals in about 55,000 U.S. households. The CPS uses the proportion of unemployed people in the sample, P hat, to estimate the national unemployment rate, P. Another example of inference settings: how much do gasoline prices vary in a large city? To find out, a reporter records the price per gallon of regular unleaded gasoline at a random sample of 10 gas stations in the city on the same day. The range, which is the maximum minus the minimum, of the prices in the sample is 25 cents. What can the reporter say about the range of gas prices at all the city's stations? So what is this sampling distribution? Let's take the average income of American households. Each March, the government's Current Population Survey, CPS, asks detailed questions about income. The random sample of 54,100 households contacted in March of 2009 had a mean total money income of $68,424. The median income was, of course, lower at $50,303. That $68,424 describes the sample, but we use it to estimate the mean income of all households. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. For the example of 54,100 households contacted by the CPS, the mean income was $68,424. The number 68,424 is a statistic because it describes this one CPS sample. The population that the poll wants to draw conclusions about is all 117 million U.S. households. In this case, the parameter of interest is the mean income of all these households. We don't know the value of this parameter. The formal definitions for parameter in statistics. A parameter is a number that describes some characteristics of the population. In statistical practice, the value of the parameter is usually not known because we cannot examine the entire population. A statistic is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. Sampling variability. How can the mean, based on the sample of only a few of the 117 million American households, be an accurate estimate of the population mean? After all, a second random sample taken at the same time would choose different households and likely produce a different value of the mean. This basic fact is called sampling variability. The value of a statistic varies in a repeated random sampling. To make sense of sampling variability, we ask, what would happen if we took many samples? Here's how to answer that question. First, we take a large number of samples from the same population. Second, we will calculate the statistic, like the sample mean or the sample proportion, for each sample. 3, we would make a graph of the values of the statistic. And last, we would examine the distribution displayed in the graph for shape, center, and spread, as well as outliers or other deviations. Sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. The population distribution gives the values of the variable for all the individuals in a population. We will be doing an activity in class where we study the population distribution using 200 poker chips, 100 of them blue and 100 of them red. The individuals are the 200 chips, and the variable we are recording is color. Our parameter of interest will be the proportion of red chips in the population, or p equals 0.50. We will take a random sample, simple random sample of 20 chips, 3 of them, here, here, and here. The distribution of the sample data shows the values of the variable color for the individuals in the sample. For each sample, we record a value for the statistic p hat for all possible samples of the same size and display them in the sampling distributions. We need to be careful. The population distribution and the distribution of sample data includes or describes individuals. A sampling distribution describes how a statistic varies in many samples from the population.